Okay, so I started to record just a little late. So after the brief description of the last lecture, and I started to recall the Legendre transform. So V is a finite dimensional vector space. F is a smooth, strictly convex function. Strictly convex means that smooth and strictly convex simply means that the second derivative in local coordinates, the matrix of second derivatives is positive definite. Okay, so the Legendre transform in this case is, I mean, in any case, it's sorry, I'm kind of stumbling. So the Legendre transform of F is a function on the dual vector space defined like this. It's the maximum over, sorry, let's call it P over V in V, P of V minus F of V. Here P is in V star. Okay, so we assume that F is smooth and strictly convex on the whole space V. So in this case, F hat, I mean, it's a theorem. Under these conditions, if F is smooth and strictly convex, we have the following. First, F hat is defined on all VDO. Second, F hat is smooth and strictly convex. Third, F hat of P is equal to P of, I mean, this maximum is achieved in this case at a critical point, unique critical point, where the star is the unique solution to the equation. I'll just write it in local coordinates. So Pi is equal to df dvi. These are not local, these are global coordinates. So here I assume that we have a basis ei in V. Vi are coordinates of V, and Pi are coordinates of P in the dual basis E super I. Okay, so I think this, oh yes, and the fourth point is the mapping P to the dual, sorry, yes, that's right, is a diffeomorphism. It's a non-linear mapping, but it's a diffeomorphism from V dual to V. Okay, So proof. I'm not going to do this. It's a homework. It's not a very difficult statement. Everything is based on the fact that F is smooth and convex, so it sort of looks like this. So in particular, it exists, this maximum exists for, this is F of V, V. So this maximum exists for any P, and it's unique because of the convexity, and it's given by this critical point because F is smooth. And then this diffeomorphism is just the corollary of smoothness and uniqueness of V star. I think there is a proof in the Arnold's book. But I'm not sure. So, but as I said, it's not a difficult proof. So this is just a recollection of the Legendre transform in the smooth, strictly convex case. As I said, F doesn't have to be smooth. It doesn't have to be strictly convex. It can be just convex. The Legendre transform in that cases may have this F dual may not be defined on the whole space. V dual maybe on some subspace. It's a very interesting chapter, the Legendre transforms, and it's very useful. As I said, it's used in optimization and thermodynamics, lots of applications.
So okay. If it stays strictly convex, but it's not necessarily smooth, then is the dual I mean, is the Legendre transformation roughly the same same regularity?
So if it's strictly convex, but not necessarily smooth.
Yeah, for example, C0, C1, so forth.
So an example of this would be, so non-smooth, something like this.
Yeah.
So, so in this case, pardon?
I'm asking this just because the homework that you gave last week was continuous, right? Oh, it was piecewise smooth, and
piecewise smooth, exactly. Yes.
The transform was piecewise smooth. So
yes.
But maybe it's not important. Okay, I shouldn't let you get distracted.
No, it's it's an interesting question, and I know the answer to this. It's in some sense it's easy to see what this is. Typically, I think in this case it's going to be defined simply not everywhere.
But you mean smoothness is needed for being defined everywhere? I thought that was only strict convexity. Or okay, because the angle.
Honestly, I don't remember.
Okay,
did you do the homework?
I did, but I got halfway, and then my train arrived at the station. I had to run home.
So well, just since we're all here, so let's we can just do it. Okay. So let's say that here f of v is v to the alpha, and here f of v is v to the beta. F check p is just max over v pv minus f of v. So so there is a critical slope here. Let's call it p0. There is a, well, let's call it p left. There is a critical slope here, p right. And so if p is anywhere great. So if P is greater than P left, you know, it's an easy exercise to see what this is. I should remember this, but because of late hours, my brain is working slow, and
Sure.
it's processing only the facts that I prepared.
Yep. Thanks. Well, I'll work it out during the break or something like that.
Okay. Okay. It's a nice, easy exercise, and actually, I advise everyone to do this. Okay, but this is kind of useless for us, because what we want to do is we want to pass from Lagrangian mechanics to Hamiltonian mechanics. Okay, so suppose that we have a Lagrangian function. So here V is vector in the tangent space to Q at the point Q. So it's a function on the tangent bundle. It's a function of two variables. So remember that last time I was analyzing the dependence on V, and we agreed that well, the kind of physical. So first we agree on the fact that these Euler-Lagrange equations are non-degenerate in the sense that there is a local solution to a Cauchy problem if the matrix of second derivatives is non-degenerate. For all V and Q. So then I kind of argued that the physical case is when the matrix is strictly positive. Positive definite. So all eigenvalues are positive. That's simply because for Newtonian mechanics, it's mv squared. So in some sense, this matrix of second derivative, its physical meaning it's the matrix of masses. One can say something like this. So we have a situation when L of VQ is strictly positive. Sorry, is smooth and strictly convex in V for all Q. That's basically, that was our assumption when we refined the information about the Euler-Lagrange equations in Lagrangian mechanics. So, which means that we can do the Legendre transform. So we can do the fiber-wise Legendre transform. L, which is a function on the tangent bundle, to H, that's the Legendre dual to L, which is a function on the cotangent bundle. And it's pointwise transform in the sense that it's the fiberwise. On each fiber, that is for each Q. So the definition, just the same as the definition above, it's the maximum over V in the tangent space to our configuration space, P of V. P now is a vector in the cotangent space. So this is the definition of the Hamiltonian function. So what else is important here? Because we have a smooth, strictly convex situation, we also have the diffeomorphism, non-linear mapping, but a diffeomorphism. Let's call it phi. For each Q, fiberwise diffeomorphism from T star to T, from the cotangent space to the tangent space, and it brings point PQ to the point V star of PQ Q. It's a fiberwise, so we don't change Q. And it's simply that V star is the critical point. So in local coordinates, we have, P in local coordinates Qi, we have Pi is equal to dl dvi V star PQ Q. So this is very nice because now what we can do, we can bring a path solution to the Euler-Lagrange equation. We can bring it to the cotangent bundle. So now let gamma Qt be a path, a parameterized path in Q, which is a solution to the Euler-Lagrange equations for our Lagrangian system. It defines the path gamma tilde, which is simply Q dot T Qt, a parameterized path in the tangent bundle. And the inverse to phi, well, the mapping, sorry, I shouldn't. So the mapping phi inverse, which is mapping fiberwise tangent bundle to the cotangent bundle, brings gamma tilde to sigma phi inverse gamma tilde, a parameterized path in the cotangent bundle. So very nice. So now the question is, can we describe this parameterized path on the cotangent bundle in some good terms? And it turns out, yes, we can. And for this, we have a theorem. That's the main theorem in Hamiltonian mechanics. If you view Hamiltonian mechanics as the Legendre transform of the Lagrangian mechanics theorem. And by the way, I will use this terminology anyway. So T star Q is the phase space. That's the standard terminology. Q is the configuration space. Where this terminology started, I actually don't know. I just never thought about this. I just got used to it. But apparently, I mean, I'm sure there was a good reason. So a path sigma in T star Q is the pre-image of a solution to the Euler-Lagrange equations if and only if it is a solution to the first order ODE, which are called Hamilton equations. And in local coordinates, Pi, Qi. So we choose local coordinates Qi and then Pi, these are global coordinates on T star Q in the basis dqi. So in this, I will still call them local coordinates because they're induced by local coordinates on Q. Hamilton equations in local coordinates, they look like this. Pi dot Q is equal to minus dh dqi pt qt, and then Q. So I'll be paying attention to upper and lower indices because when we do coordinate transformations, the coordinate transformations are from the Lie group GLM. And for GLM, there are two representations, non-isomorphic, the vector representation and dimensional, and it's dual, and they are not isomorphic. And this is why in geometry, sometimes it's useful to have upper and lower indices that shows these local coordinates, they transform according to the vector representation or to its dual. It's the indication of the way how local coordinates change. So we will give these equations a name H. So once again, this sigma is a pre-image of a solution to the Euler-Lagrange equations, if and only if it's a solution to the Hamilton equations, to these equations. So that's a powerful theorem. And again, I'm not going to prove it. It's a nice and very straightforward exercise, simply based on the explicit formula for the Hamiltonian Anyway, so let me leave it as a homework exercise. We can have a session one of those days which will be convenient for all of us, where you can ask questions about homework and so on. So it's just some kind of informal discussion session. We can do it. Yeah, I think the best thing to do is probably I'll send a doodle about this. I have 11 notifications. Jeez, and they're coming. Sorry, I'll switch off the phone. Okay. So this proof is a homework, but now let's look at the consequences. So first, Hamilton equations are first order equations, and there are 2n equations for 2n unknowns. The right number of equations. Euler-Lagrange equations are second order for n equations. I mean, n equations for n unknowns. So what we did is, in a sense, we doubled the number of equations by reducing the order of the equation from the second order to the first order. So, second, Hamilton equations are first order. So I just want to emphasize this again and again, which means that they can be regarded, they are equations, geometrically, they are equations for flow lines of the vector field. I can write it in local coordinates. So it's a vector field which, so it attaches a tangent vector to each point of the cotangent bundle. And it's dH dPi dQi minus dH dQi dPi. And it's in the tangent space point PQ to the cotangent bundle over Q. So just remember that if you have a manifold M local coordinate system, if you have a vector field, which is a section of the tangent bundle, oops, not QM. So for each X being section of the tangent bundle, it simply means that for each X, it produces a tangent vector to M. And since we choose local coordinates, this gives a basis di in the tangent space to X, and then we can write V in terms of this basis. And this is what I did here. So now we have local coordinate system Pi and Qi, and this is this standard basis that you have in the tangent space if you choose local coordinate systems on the manifold. Local coordinates on the manifold. So, in other words, so Hamilton equations as equations for flow lines can be written as ddt pq is equal to vh pt qt. It's just for any m, for a manifold and vector field, such equation would be dxt dt equals vxt. And I simply use it, wrote it using the coordinates pq. Okay. Any questions so far? So let me ask questions. So Cheng Zhao, are you a graduate student or an undergraduate student? Hello?
I mean, I can answer that question for him, but I think he wasn't aware that maybe you were talking to him.
Ah, okay. I mispronounced his name badly.
He's a grad student.
Okay. And Haoli,
Postdoc.
are you postdoc? Okay, so we don't have undergraduates. Very good. So then let's move on. So now, very important definition. Function f on the cotangent bundle to, yes, so just a real valued function on the cotangent bundle is an integral of motion, or constant of motion, as it's called. These are called, they called in mechanics. If f is constant along any solution to Hamilton equations. It would be the same for, it's just if you have a manifold, like in this situation, a vector field. So if you have a function on M, it's an integral of motion for this vector field if it's constant along the flow lines of this vector field. And now we have a, just as in case of any vector field, we can have a simple criterion for f to be an integral. So let's differentiate f. And again, I could have done it with any other vector field, but there's a nice specific feature of this particular vector field. So we want this to be constant. So first we want to find the derivative, and then we say it's 0 for integrals of motions. But let's first find the derivative. So using the chain rule, we write this. Then using Hamilton equations, we can write this as minus dh dqi df dpi dh dpi df dqi. And what this is the Lie derivative of the function f along the vector field v. So it's and of course it's an interesting combination over here. So let's give it a name. Let's define so-called Poisson bracket for T star Q. It's the bracket between two functions, H and F. And it's just this expression, dpi df dqi. So when I'll finish with the Hamiltonian reformulation of Lagrangian mechanics, we will make a digression into symplectic geometry, and I'll define more general structures, of which these are very important examples. But for the moment, let's just do everything in local coordinates. So it's the first statement, just a remark. It doesn't depend on the choice of local coordinates. You choose another system of local coordinates. On the overlap of these two coordinate systems, the coordinate transformations for the derivative in P will cancel the coordinate transformations, the Jacobian for the derivatives in Q, and the expression will stay the same. So it's globally defined. And we will see how to do it in coordinate-free form. So now you can see that, well, now you can see that we proved the following theory. F is an integral of motion for Hamilton equations if and only if the Poisson bracket between H and F is 0. And you see, this is absolutely beautiful because we started with differential equations, which is analysis. And now it turns out that there is some kind of criterion that looks algebraic. Just this expression should be 0, and then it's an integral. So corollary, an important corollary, H itself is an integral. So simply because H with H is 0, because this bracket is skew-symmetric. So the physical meaning of this is the conservation of energy. And the physical meaning of H is the energy function. But I'm not going to argue why, you know, if it start to talk about energy, first I have to overcome a philosophical dilemma. What is the energy? Is this a quantity or it's an abstract notion? Does it really exist in physics? Well, every physicist, well, I think everyone knows what the energy is intuitively, but it's hard to say exactly what it is. It's more like our abstraction to a large array of phenomena, and it's a formalism that allows us to describe certain physical features in a uniform way, but it's not necessarily something that really exists in nature, like a brick or a particle, something that can be detected. It requires a certain level of abstraction, the same as straight line. I mean, straight lines, I'm not sure you never saw straight lines in the nature. They're all wiggly. But in our mind, there is a straight line. That's the abstraction for all wiggly lines. The same thing probably about the energy, but again, then we will turn into philosophy class. We don't want this. Okay. So any questions so far?
A philosophical one.
Yep.
Are there, I mean, so is the conservation of energy then, because the way that you described energy made it sound like, okay, so if it's something that you can detect out of a physical system, then presumably it's some sort of invariant.
Yeah.
And so what does conservation mean here? Because I assume that it's not tautological in the sense of like whatever preserves that invariant, maybe change of coordinates or so forth. So this conservation is with respect to?
Well, in conservation with respect to the dynamics, it's preserved by the dynamics.
Okay.
So if we say that it's the energy, then we have a conservation of energy. Why it's the energy? Again, that's a long philosophical debate, and I don't know what is the best way to give kind of meaningful arguments in favor of this, because you know, this is the realm where there are no proofs. I can only say the following, that conservation in this context is identical to being an integral. This quantity is preserved along the trajectories. It's a closed system, so you consider closed system. So if we say that this is the energy of a system that's isolated from the rest of the world, physically it sort of makes sense. Then the energy should remain intact. And finally, if we consider the case when Q is, say, Rn, and the Lagrangian is mv squared over 2 minus the potential energy, then the Hamiltonian, if you will do the Legendre transform, it will be the sum, p squared over 2m plus v squared. And it's been argued a long time, a couple of hundred or maybe 300 years ago, that this is the energy of motion. So it's kinetic energy. And this is the potential energy. And physical philosophical meaning of potential energy, I think of it like this. It's the energy that can be potentially released. But maybe it's a misinterpretation of the word potential. But say, what does it mean potentially released? If you have a particle moving in the force field with this potential, then it will feel the reaction to this potential energy. I don't know. It's see the I'm sending you to the hardcore physics mechanics class book, Landau and Lifshitz, Volume 1, Classical Mechanics. They talk about energy a lot. So now let's forget about physics and let's give a definition, a very important definition for the future. So A is a Poisson algebra if A is a commutative algebra if A is a Lie algebra. So we have two algebraic operations on the same vector space. Let's write it AB, the Poisson bracket. And if the Lie algebra structure acts by derivations on the commutative algebra structure. So what does it mean? It's a Lie algebra. It means that it's skew symmetric. And the Jacobi identity holds. Acting by derivations simply means that we have a Leibniz rule. We have the Leibniz rule for the multiplication. So this is a definition. And an example, let's take C infinity functions on the cotangent bundle with the bracket that I just wrote above, F1, F2, df1 dpi. I think I forgot the sum, but I assume that there is a sum. df2 dqi minus df1 dqi df2 dpi. Okay, so homework, check that this is a Poisson algebra structure on C infinity T star Q. Okay. So, any questions? Okay, if there are no questions, then let's start a new chapter. So let's start a digression into basic notions of symplectic geometry. So last call for questions. No? Okay. So basic notions. In symplectic geometry. And then next time I'll formulate Hamiltonian mechanics in the most general case when it's a smooth Hamiltonian dynamics on symplectic manifolds. And we will continue with the Hamilton-Jacobi principle and so on. So I think we still have about 2 lectures on classical mechanics, and then we will switch to quantum mechanics. And then after quantum mechanics, we will see how they are connected. Classical Hamiltonian mechanics and quantum mechanics. So that's the goal of the course. Okay. First, the definition. Let M be a smooth 2n-dimensional manifold, even dimensional. Omega is a 2-form on M with real coefficients. So this pair is called a symplectic manifold. Omega is a symplectic structure on M, or it's also called symplectic form. If omega is closed and if it is non-degenerate. Non-degenerate means that, say, in local coordinates, if you write this form as sum over I less than j, dxi dxj, then determinant of omega ij, this q-symmetric matrix. So maybe I should. So it's as usual, it's a q-symmetric matrix, which I can write like this. This should be non-zero. Equivalently, in a coordinate-free form, since omega is a 2-form, it defines a mapping from the tangent bundle to M to the cotangent bundle. It's just you can pair, so omega of V in local coordinates, it just simply means that you take sum over ij and you pair, say, let's say that this is the omega at the point x. This is a vector field at the point x. So it's just the contraction of the 2-form with the vector field V. V is a section of the tangent bundle. So we always have this mapping. And the non-degeneracy means that, so non-degenerate actually it means this. So equivalently it means that omega is invertible. So it gives an isomorphism of the tangent and the cotangent bundles. Okay, so examples.
Sorry, is that dxi or dxj?
Sorry.
Oh, okay. V. Okay, yeah, sure.
Yes. I mean, it doesn't matter. Since it's q-symmetric, you can either pair it with the left or with the right component.
Yep.
So examples. First, let's start with the simplest example. M is just R2N with coordinates PI, QI, global coordinates. So then omega is sum over I from 1 to N, dPi, dQi. So you can easily check that it's not degenerate. So it's the matrix omega ij is just this matrix. So this is for P and this is for Q. and its determinant is non-zero. Second, and of course, in this example, you can think of this example as M is the cotangent bundle to a vector space, and it's an n-dimensional vector space. If you choose a basis in V, you choose an isomorphism. V, you choose an isomorphism between V and R2M, and then M will be, because for the vector space, this bundle is trivial. So, so this M will be R2N with these coordinates P and Q. P along the cotangent directions and Q along the Rn, along the V directions. And the second example of the same nature is just replace V by any manifold. So then let's choose local coordinates on Q. So, so then this gives global coordinates on T star Q for every cotangent direction. So in this local coordinates, we'll define the symplectic form in the same way, dpi dqi, and it's actually, it's defined globally, in the sense that if you change the coordinates, it's going to be given by the same formula in any other local coordinates on Q. So, so these are the two basic examples, and we will see more examples later. So, well, actually, why not? So here's one more example of a different nature. So let's consider S2 as a sphere of radius R in R3. And let's define the form omega, which is epsilon ijk, is totally skew symmetric tensor dxi dxj xk. Homework: prove that omega gives as, well, let's say omega is a symplectic form on S2. So this this symplectic structure is closely related. I mean, it's actually naturally related to the Lie algebra SO3. But we will discuss it later. So this is these are the three examples, the definition. Any questions about the definition? I mean, maybe it looks strange at first, but at least it's something very natural. It's a closed form, and it's non-degenerate. So then maybe I should make a remark. If omega is closed but degenerate, there are such things. So this this pair is called presymplectic. And there is a way how to do, so there is a way how to make a smaller symplectic manifold out of it. We will discuss it later. Okay, so no questions?
What do you mean by smaller? I mean, you're gonna say it later, maybe. But...
Yeah, smaller, let's say, in local coordinates, it's just have fewer local coordinates.
Okay, so
of less dimension.
okay.
That's what it is. So this is called symplectic reduction. So it's going to be not a submanifold, but it's, so one can construct a projection from M to something that is, in good cases, is a symplectic manifold. In bad cases, it's something wild. So it's, we'll see. So I want to make, I think we should finish soon. I forgot, if we stick to the usual Tsinghua schedule, when should we finish? Yeah, what's the timetable?
Yeah, I'm trying to remember because I don't usually. It's okay. I don't know. It's 50 minutes off. Oh, how many minutes?
55.
55.
Yes.
Oh, thank you. Okay, so so we're already over time.
I think it's
20 plus 40. Yes. No, it cannot be
He
50.
means he means
40.
stop at 8:55.
Ah,
Like
okay. Okay.
like we skip the break.
So let's not, I didn't make a break, so it's 9:50. So maybe I should, yeah, let me define a couple of notions and then we will make a break until next week. So two very important types of submanifolds. First type, definition. Yeah, let's define it. Let's define it like this. N in M is an isotropic submanifold if isotropic submanifold for the symplectic structure omega on M. If omega is vanishing on any pair of tangent vectors to N. So N is a submanifold in M. So for any point in M, the tangent space to M is a subspace in M. So it's isotropic if we have this property. So let's formulate it in an equivalent way. So equivalent definition. So let's see, what do we have? I'm just trying to, yes, so we have a, so N is a submanifold in M. So we have a, tangent subbundle. So for every X in M, we have a tangent subspace in M. So then we have the subspace in the space, in the cotangent space of linear functions on CXM, which vanish at every tangent vector in N. So it's an orthogonal subspace to the tangent space to N, but because we don't have the natural scalar product, this orthogonal subspace is not in the space itself, but in the dual space. Okay. So we have this, and we also have, since we have the symplectic structure, we have a mapping of the tangent bundle to the cotangent bundle, and we have the image of the tangent bundle to N. So we have this subspace. And so we have two subspaces in the cotangent cotangent space. And they can be completely arbitrary, or they can be ordered by inclusion. And the equivalent definition of being isotropic is the following. So the image of the tangent space is inside of the orthogonal subspace to the tangent space. So it's all in the cotangent space to M. And just it's obvious that this definition is equivalent to this one. These are equivalent definitions. Maybe a little homework, if it's not obvious now, then prove, well, there is nothing to prove, just see that's equivalent. And to the first definition. But then you see, very nice. So we defined isotropic submanifolds for this particular inclusion, but they can be ordered in another way. So we may have a different inclusion, and that's called coisotropic. If we have opposite inclusion. So first remark that these are special submanifolds. These are special cases of how these two subspaces are positioned against each other. In general, there are no inclusions. So this is actually a special and strong property, that you have inclusion either in one direction or in the other direction, so that you have either isotropic or coisotropic. And then So then another remark. If n is co-isotropic, what can we do? We can, so n is a submanifold in M, so let's say that omega n is the pullback, or kind of in plain language, it's a restriction of omega to n from M. So a little theorem, which is easy to prove again, and let's say it's a nice homework. N with this two form is a presymplectic manifold. In other words, d omega n is closed and omega n is degenerate. So why it's closed? Well, I'll spoil the fun. So this is because restriction commutes, or pullback commutes with the Ram differential. And this is just fine zero directions. And that will complete the proof. Okay, so I introduced this notion. So next time we'll have a brief repetition of this. I'll give examples of isotropic and coisotropic submanifolds. And we'll discuss a little more the symplectic geometry, the examples. So, you know, maybe just before we'll finish, I have to introduce this very important notion. I forgot, most important notion. So the notion of Lagrangian submanifold. N in M is Lagrangian, a Lagrangian submanifold. If N is both isotropic and coisotropic. And just a little spiel about the dimensions. So if N is isotropic, its dimension less or equal than half of the dimension of the ambient symplectic manifold. And is coisotropic, then its dimension greater or equal than n. And if n is Lagrangian, the dimension is exactly n. And we will see that, remember this, we had this discussion of variational boundary conditions. So we will see that in the Hamiltonian framework, variational boundary conditions, they're simply Lagrangian submanifolds with certain properties. So it's a very nice language to for these purposes. Finally, just before the end, I will make a remark. So I've made an assumption that M is even dimensional, and it's obvious that it must be even dimension if you want to have non-degeneracy. a skew-symmetric matrix in the odd dimensional vector space will always have 0 determinant. So this is this even dimensionness is forced by the non-degeneracy requirement. Okay, so I think that's the end for today. I hope it's all useful, in the sense that I hope I'm not repeating something that's that you know quite well. Okay, it seems like I do repeat something that you know quite well. Okay, well, I don't hear anything.
It's useful. Thanks.
Okay. Okay, so we'll see you next week.
All right.
Okay,
See you.
bye-bye. See you.
Thank you.
You're welcome.